Hi, my name is Insung Kang from Georgia Tech, and I'll be presenting our work where we investigate a biomechanical effect of providing a hip assistance that scales with different incline levels using a powered hip exoskeleton. So, over the last decade, we've seen different research groups being successful in developing exoskeleton that can augment humans for improved mobility. Especially, researchers explore different control methods to optimize exoskeleton assistance strategies to maximize the human exoskeleton performance. And through this, we have seen fantastic results across different groups, such as reducing the user's energetic demand during locomotion. One common story that we're seeing from most of these exoskeleton studies is that there is some sort of optimal assistance level for a given condition. And this optimal assistance level is correlated with the user's biological demands, such as joint biomechanics. However, most of these studies were often conducted at very specific conditions and really does not capture what a user might experience in a realistic setting like outdoors. In a real-world scenario, a person continuously modulates what I like to call it a user state variable. These variables can be both internal, like the user's walking speed, or external, like different locomotion modes. One thing to note is that during these dynamic movements, the user's biological demand will constantly change. A good example is when walking up the ramp. Looking at the user's biological hip joint moment, we can see that there is a greater demand in the hip extension moment as the ramp incline level increases. So this brought up a research question to us. Do we need to scale the exoskeleton assistance such that it aligns with the change of the user's biological demand? We hypothesized that providing hip assistance during uphill walking that scales relative to the incline levels will have a greater reduction in the user's biological demand compared to providing exoskeleton assistance that is nominal across all inclines. And this biological demand refers to the user's biological joint moment and the corresponding muscle activation levels. To answer this question, we utilize a powered hip exoskeleton along with a standard biomechanics tool such as force plate, motion capture, and EMG sensors to measure the user's joint biomechanics and EMG levels. We recruited one able-bodied subject walking up a ramp at 4 different incline levels with our powered hip exoskeleton. During walking, we provided hip assistance that scales with a change of incline levels, where the assistance level was set to 20% of the user's biological hip joint moment. Additionally, we had a static assistance condition where the assistance level was set to be a nominal level across all inclines. Lastly, we had a zero impedance condition where the exoskeleton was controlled to be transparent to the user's movement. Our preliminary results indicate that our scaled assistant was able to reduce the user's hip extensor activity, mainly gluteus medius, on average by 11% compared to no assistant across all inclines. However, similar results were not shown in the static assistance. Generally, we observed that the scale assistant benefit increased with higher incline levels. So let's look at the case of highest incline levels. The scaled assistant clearly showed a greater EMG reduction by 30% compared to no assistance. However, interestingly, we observed that the reduction in the hip extensor EMG did not directly correlate with the reduction in the hip joint moment, and rather the amount of exoskeleton benefit was smaller. This phenomenon may be explained by the contraction of the antagonist muscle, and indeed we observed that the hip flexor EMG, mainly rectus femoris, increased during these conditions on average by 15% for the scaled assistance and 24% for the static assistant compared to no assistance. Our preliminary results indicate that providing scaled assistance can help the user in reducing the corresponding EMG level. Interestingly, we found that the assistant benefit in EMG did not directly correlate with the user's joint moment, and this was explained by the muscle co-contraction during the assistance. From this, we can see that not only did the scaled assistant outperform the static assistant by reducing the hip extensor EMG, it had a lesser effect in the antagonist muscle compared to the static assistance. So what are the next steps? Along with increasing the subject numbers for our study, we think that more in-depth analysis and evaluation in both biomechanics and energetics should be done. Additionally, we can expand our study approach to see if similar biomechanical results are shown in other locomotion modes such as stairs. Lastly, given these findings, we can focus on implementing these scalable exoskeleton control strategy to continuously modulate the assistance level for evaluating the exoskeleton performance in a more dynamic and realistic settings. Thank you.